We ready? All right. Chapter 8, periodic relationships among the elements. Mendeleev, he started with his periodic table. It was wrong because it was based on atomic mass, right? There's some inversions where just because of the isotopes abundance, it's out of order. So Moseley came along. He was able to figure out the positive charge of the nucleus. From that, he was able to figure out the protons and how many protons were in each. So he he righted the periodic table so that it increases by atomic number. And that's what our periodic table today is, determined by the number of protons that something has. Representative elements, those in general are the ones in the S and the P blocks. All right. The S and the P blocks, there's no exceptions. They kind of do what they're supposed to. Where we have exceptions in the D, we have exceptions in the F. Right. Valence electrons, we know these are the outermost electrons. These are the ones that have to do with bonding. Core electrons, those are the inner shell electrons. Those are the ones that are responsible for the shielding effect. What's the shielding effect? Yeah, like the nucleus is trying to pull the electrons in. It's positively charged, trying to pull in those negative electrons. The more core electrons, the more those outermost electrons get shielded from the nucleus. And that's going to be effective nuclear charge that we talk about in a minute. What's isoelectronic mean? Same electron configuration, same number of electrons. So something like neon is isoelectronic with the fluoride ion and with the sodium ion, right? They all have 10 electrons. They're not the same because they have a different number of protons, but they end up being isoelectronic, meaning having the same number of electrons. All right. All of these can be explained if we just understand effective nuclear charge. That's all we have to understand, and then all of these make sense to us. Effective nuclear charge. We have the nucleus in the center. All those core electrons around it. All right, think about the outermost electrons there. They don't feel the same pull because those ones in the middle kind of blot it out, right? It's almost like if it's light trying to get out of the center, the more stuff we have in between, the less light we're going to get on the outside. Right? So what happens is if we have a lot of shielding effect, there's weak attraction between the nucleus and those outermost electrons. If there's limited shielding and we have a lot of protons in the nucleus, it really pulls those electrons in tight. So if we can keep that in our heads, as we go across a period, we're adding protons to the nucleus, we're adding electrons, but we're adding outermost electrons, we're adding valence electrons. So the shielding effect doesn't change. The shielding effect doesn't change, but we're adding more protons. So what ends up happening to those outermost electrons? They get pulled in tighter. If we understand that, we can understand then that ionization energy must go up as you go across. Why? Because as you go across, you're pulling those electrons in tighter, it's harder to steal an electron away. What happens to atomic radius as we go across? Decreases. Why? Because I'm pulling the electrons in tighter. Electron affinity, that's the energy change when an atom pulls an electron from somewhere else. If I'm pulling electrons in, it's not just my own electrons, it's other electrons. Electronegativity, right? We know fluorine has the highest electronegativity. Why? It has the highest effective nuclear charge because it's pulling those electrons in from those outermost electrons in. As long as we understand that, all of these make sense to us. That's going across. As we go down, what's happening? We are increasing the number of protons, but we're adding energy levels that are farther from the nucleus that's going to increase shielding. And we increase the shielding faster than it increases the pull from the nucleus. So as we go down, the effective nuclear charge decreases. So what happens to atomic radius? Atomic radius gets bigger more because we're adding more energy levels, right, farther away from the nucleus. What happens to our ionization energy? It's going to decrease as we go down. Why? Because the electrons are farther out. There's greater shielding effect. There's less pull on the nucleus. It's easier for somebody to come along and steal an electron away. Right? As we go down the group, electron affinity decreases. It's not trying to pull those, it can't pull those electrons in tight enough to steal somebody else's electron. Right? Even non-metallic character, metallic character, we haven't really talked about that, but in general, our nonmetals want to gain electrons, right? Our metals want to lose electrons. Why? It has to do with effective nuclear charge. As we go across, the effective nuclear charge is increasing. So it's starting to, instead of wanting to lose those electrons like the metals, they want to gain electrons. That's non-metal characteristic. Metallic character, it wants to lose those electrons.
Atomic radius and ionic radius are just the same thing, but an ionic is like F minus versus F.
Yeah, so we can't, there's not like a general trend like this because the metals lose electrons. So whenever we lose electrons, we get smaller, right? Because we're going to lose a whole energy level. There's less repulsive forces there, and we're going to pull the electrons in tighter, so it's going to get smaller. Nonmetals, whenever they gain an electron, we're going to increase our repulsive forces because there's more electrons there, and they're going to spread out, and we're going to get bigger. So, what else we got? As we go down group one, we said the ionization energy decreases. So what that does is that makes it more reactive as we go down the group. We showed like a super old video. The guy was putting like a sample of sodium in metals, so a sample of potassium in metal. And by the time he got down to cesium, he put the cesium in the metal, and it went and like exploded the glass beaker. All right. Why does it get more reactive? It's all based on that ionization energy. The lower the ionization energy, the more reactive it is. It's easier to lose an electron. If it's easy, that's going to speed up the reaction, and we're going to end up having a violent reaction as we go down here. The halogens are the opposite. Why? Are they trying to lose electrons? What are they trying to do? Gain electrons. So as you go up, they become more reactive. Because fluorine has the strongest pull from the nucleus, it's really going to pull other electrons in. So it becomes more reactive as you go up, the halogens, versus as you go down, the group 1 metals. Right? All of this based on that effective nuclear charge. If we can understand that finally, right, then we can understand all of these. It's not just random atomic radius decreases as you go to. If you understand effective nuclear charge, we can understand all of these trends. Properties of each elemental group. I would just say like group 1 and group 2, those are our reactive metals. All right, alkaline metals, alkaline earth metals. Our noble gases, all right, we know that they have a full outermost energy level, so they don't tend to form bonds with anybody. Halogens, and then we don't really name the rest. We call these the transition metals in the middle, intertransition metals down the bottom. All right. Chapter 9. This is us getting into bonding, right? We got our Lewis dot symbols. We just put electrons around however many valence electrons. Ionic bonds, lattice energy. I feel like I've talked about lattice energy so many times, and we still get tripped up on it. If I had two formulas, NaCl and MgO, which one of these is going to have a higher lattice energy and why? Why MgO? +2, -2. +1, -1. So the more positive charge that is, kind of like the denser that positivity is, the more attracted it's going to be between the Mg and the O. So what is that going to lead to? A high lattice energy? That's going to lead to a high melting point, a high boiling point. It's probably going to tend to be harder than other materials. Might be insoluble in water because it's attracting to that other ion much stronger. No, they're related, but like usually ionization energy we're talking about for a particular atom versus a compound here for lattice energy. What if I had CaS? Which one of these two has higher lattice energy? All right, so what's the difference? They're both plus 2 minus 2, right? So what's our second factor we look at? The size of our atoms. The smaller the ions, the more concentrated that charge is, the stronger the attraction, right? If we spread this plus 2 charge over a much bigger volume, it's not going to have that same charge density to it, right? So we want small, highly charged ions. That'll give us the highest lattice energy. Who would have the higher lattice energy between NaCl and CaS? CaS, right? Charges first, then we look at the size second. And that's only for, we use it in the context for ionic bonding for the charges there. All right, then we get into covalent. Lewis structures, super important we can draw Lewis structures correctly, right? We got to count up electrons. We can't just assume, I feel like putting a couple electrons around this guy, maybe a double bond over here, right? We got to go through and make sure we count up the electrons. Formal charge. So when do we use formal charge? Is when we have something like this. Right. Which one of these is more likely? The question might be, using formal charge, prove which one is more likely to occur, more plausible. All right, how do we calculate formal charge? Formal charge is equal to valence electrons minus number of unbonded electrons minus the number of bonds. Right? Unbonded electrons, number of bonds. So if we do it for this top one here, both oxygens are the same. Right? The oxygen's formal charge is going to be 6 valence electrons, 4 unbonded electrons, minus 2 bonds, 0. So this one is 0, that one is 0. Carbon, how many valence electrons? 4, minus 0 unpaired electrons, minus 4, 0. All right. So that one looks pretty reasonable. Why does that one look reasonable? All formal charge formal charges are 0. How does it change for the second one? Here, this oxygen, 6 valence electrons, minus 2 unpaired electrons, minus 3 bonds. I get a plus 1 there. Carbon is bonded the same way, right? It still has 0 unpaired, and it has 4 bonds. So that one is going to be 0. This oxygen, 6 valence electrons minus 6 unpaired minus 1 bond, minus 1. So which one is more plausible? This top one. There's nothing wrong with this one, right? This one still, everybody's following the octet rule. It still works out. But this one is more plausible because we get our formal charges down to 0. We only have to worry about formal charges when they say prove using formal charges. Yep. I hope so. All right. Bond length. Of these bonds here, which one would be the longest, which one would be the shortest bond? What does the bond length have to do with? The more bonds that are there, that means there's more electrons between those two atoms. The more electrons we have, the more negative charges, right? That's going to pull those nuclei a little bit closer together. The nuclei repel each other. But if I add more electrons there, because I have a double or triple bond, that increases the shielding effect between them, and they can get a little bit tighter together. Single bonds, that's going to be the longest bond there. Resonance structures. So resonance structures, that's when we have something like this. Right, when we have to choose where that double bond is going to occur, we need to draw all those possibilities. Why? None of these represent this molecule well. Does this molecule have one double bond and 2 single bonds? It doesn't. What does it have? it has like 1 1/3 bonds everywhere. It's like that double bond is equally spread out around that whole thing. So not one of these works together. It works a little bit better. When will we have to draw resonance structures? When it has to draw resonance structures. All right. Electronegativity, right? That's going to help us determine polarity later. We'll talk about that when we get there. Incomplete octet. Who can form an incomplete octet? Or who likes forming an incomplete octet? Incomplete octet? Who likes to form a duet? Hydrogen. Hydrogen forms 1 bond. Right? It's happy with just 2 electrons. Instead of octet, instead of 8 around it, it's happy with just the 2 around it. If we're going along that top row there, we go to beryllium. Beryllium, a metal, but it tends to form some covalent compounds. When it does, it only likes to form 2 bonds. Boron, right? Again, that's a semi-metal, but when it forms covalent, it likes to form 3 bonds. After that, we got our octet. All right, carbon likes to form 4, and everybody else likes to form 4. The reason why those only form like 1, 2, or 3 bonds is they're just smaller. There's less of a pull from the nucleus. It's hard having all those electron clouds moving into that. All right, who can have an expanded octet? No, some noble gases. What's the rule for expanded octet? Anything from phosphorus on. All right, I'm going to say bigger than phosphorus. When I say bigger, I mean higher atomic number. All right, so phosphorus can have an expanded octet, and anybody after that. Again, we're only talking those few. Where's our periodic table? Right. Well, we're talking covalent compounds. We're really only talking about those guys and hydrogen, right? So from 15 on, right? So it's kind of like we're just saying those are the ones that can have an expanded octet. It's really rare for a noble gas to form anything. So it's only a handful that we really have to worry about. Bond enthalpy. This is the only place all year. It's reactants minus products. Everywhere else it's final minus initial. Products minus reactants. And this is a way for us to get our delta H, our enthalpy change. Reactants minus products. All right, why is it this way? Here, we need to break bonds. Breaking bonds is an endothermic process, right? That portion of it is a positive value. It takes energy to break those bonds. Forming bonds is an exothermic process. Delta H is negative. So that's why we have the reactants minus the products. Whatever the bond enthalpies are, or bond energies, bond dissociation enthalpies, they call it a whole bunch of different names, right? Whatever it is, it's products or it's reactants minus products here. Everywhere else, products minus reactants. This is a way for us to look at delta H. Why was it in this chapter? Because we have to draw out that structure, figure out how many bonds there are, how many bonds break, and what new bonds are formed. Determining which one is larger will determine whether if we took more energy to break the bonds, our overall enthalpy change is going to be positive. If we got more energy out, right, we're going to be exothermic. Chapter 10, chemical. So just moving on from taking it a step further, now we're looking at our molecular geometries. We use the Vesper-Sepper theory, where electrons just try to get away from each other, right? They repel each other, and they try to get away. So we end up with groupings here. Right. This is the number of electrons coming off that central atom, number of directions. If we're going off in 2 directions, they're going to get as far away from each other as possible, and we're going to be linear. Trigonal planar, we have electrons coming off in 3 directions. It doesn't matter if there's actual elements there, atoms there, or if it's a lone pair. We're just counting up electrons coming off that central atom. Trigonal planar, what's our angle between those? 120, it's flat, it's planar. If I replace one with a lone pair, that's probably going to make my angle a little bit smaller, right? Those electrons now only belong to that central atom, so it gets a little bit closer to that central atom, so it's going to push those remaining electrons a little bit closer together. 4 directions, we have our tetrahedral, right? Not 90 degrees. We're about 109.5 here. If we replace one, right, now we have trigonal pyramidal. It's like a pyramid, still in the shape of the triangle. Those bond lengths now are a little bit shorter, all right, that angle. That bond angle probably now around 107, 107.3. If I replace the second one, like what common molecule? Water, thank you. Like water, right? Now I'm down to like 104, 105 angle there because I have 2 lone pairs pushing in there. 5 directions. 5 directions, I'm going to picture I have a linear molecule, right, at the axes, and then I have a trigonal planar molecule right at the equator. That's what I have for my trigonal bipyramidal 5 directions. And then when I start to take atoms off and put lone pairs, I always take them from the middle. I replace one, it looks like a seesaw. I take another one, I'm in the shape of a T. I take another one, I'm linear. 6 directions is rare, right? We got octahedral, right? And we see the other ones that are there. Dipole moment, polar molecule, super important. It's going to take what we did with our Lewis structures. We're going to factor electronegativity. We're going to factor the shape into it. And eventually in chapter 11, that's when we get into all those intermolecular forces and how it affects viscosity, boiling point, melting point, all those properties. Right? But it's really important we get the Lewis structure right, we get the shape right to determine whether it's polar or not. In general, when we have lone pairs of electrons on the central atom, that tends to be polar molecules. When we have no lone pairs on the central atom, those tend to be nonpolar. There's exceptions to both rules, but in general, if we have no lone pairs, we're nonpolar, lone pairs, polar. We could have something that has, like ozone, is 3 oxygens, right? Something like this. So even though there's a lone pair, since they have the same electronegativity, it's a nonpolar molecule. For these ones, we could have something where we have, right? It's still linear. There's no lone pairs, but since we have different poles on the outside, we're going to end up pulling the electrons in that direction and being polar. Right? But in general, nonpolar for the no lone pairs are polar. All right, hybridization. What do we need to know for hybridization? The amount of directions electrons are coming off the central atom. So if they're going in 2 directions, what do we write for hybridization? sp. They take an s orbital and a p orbital, and they hybridize to form 2 identical orbitals. How about 3? sp2. They take 1 s orbital and 2 p orbitals and make 3 equivalent ones. Here, sp3, and then we don't assign them to 5 or 6. Right. Pi sigma bonds. Okay. All single bonds are sigma bonds. The first bond between any 2 atoms is sigma. Anything after that is a pi bond. So you can only have 1 sigma bond. Anything after that is pi. So if I look at this molecule here, this HCN, between the carbon and the hydrogen, that's going to be a sigma bond. Between the carbon and nitrogen, one of these is a sigma bond, and the other 2 are pi bonds. It's tough for the triple bond, but it doesn't matter which one you say is sigma, which one you say, as long as there's 1 sigma and 2 pi bonds there. All single bonds are sigma. The first bond there is always sigma. After that, the rest are pi, whether it's a double bond or triple bond. Molecular orbital theory. delocalized molecular bonds. Right? This is what explains my resonance structures. Right? Though that bonding pair there, that double bond, isn't uh, isn't locked in between that sulfur and that oxygen. Instead, it's free to move about the whole molecule, creating a molecular orbital. Instead of an orbital, a bonding orbital just between them, it's across the entire molecule. And what does it do? It just adds some stability to the molecule, and it's a way for us to explain our one of the third bonds up there. All right, anything on chapter 9 or 10?